like this is a little bit, intimate, there's 10,000 people who are watching this live stream. So, yay.
Yeah.
Nice.
All right, thank you all.
Thank you. Okay, on to our next solo presentation. We have Mathieu from Kakarot. I'm totally saying that wrong. You're going to correct me, right?
Everyone. I'm super happy to be here, and I'm going to present you and talk to you about Kakarot. Kakarot is a company that is building efficient and secure EVM probability solutions for various technology stacks, but mostly using the Starknet stack and the Starkware technology. So just for some context about Kakarot, Kakarot was initially a project of the Starknet ecosystem and later evolved to be a full-fledged ZK EVM and EVM probability solutions. Why? Because we believe that all software will eventually be provably secure, and we believe that Ethereum and Bitcoin together are going to be the settlement layers of the internet. And as Vitalik said a few months ago, probably in a few years, all rollups are going to be ZK rollups. And we agree with that take, and we're building with this vision in mind. But ZK rollups are, or had until now, some user experience hiccups, let's say. And that's why optimistic rollups until now had the lead on the UX and usage of ZK rollups. But ZK rollups have major advantages, and we want to see these advantages more represented in the real usage of Ethereum rollup technology. These advantages is the increased scalability, because you can totally parallelize the proving of your ZK EVM or your ZK VM. And unlike with optimistic rollups, you don't have the requirement of locking a lot of capital for economic security of your rollup. And finally, one of the major drawbacks of optimistic rollups is the long finality time. You have to wait until the dispute window is over for your funds and your transactions to be considered final, which can take up to 7 days. And ZK technology allows you to bring that time window down to a few hours and maybe a few minutes in the future. But ZK EVMs have a lot of limitations. They're expensive and they're hard to maintain because you need a lot of engineering resources, and the Ethereum protocol and the EVM is constantly evolving. So when you're building a ZK EVM, you need to build an EVM thinking about the fact that that EVM is going to change a lot in the next years, and you need to be able to maintain that EVM. And EVMs might run into problems when you're developing your EVM to target a specific kind of prover, and that prover ends up being not efficient enough compared to the competition, and you always want to make sure that you can transition your technology from one prover to another, which is kind of what we're doing at Kakarot, because Kakarot is currently proven using Starkware's Stone prover, but the Stu prover is coming in the next month and will bring up to 100x or 1000x improvements over the current prover. And because of our architecture and tech stack, we'll be able to benefit from these improvements from day one, and that will considerably change things about the position of Kakarot in the ZK EVM landscape. So there are different ways of building ZK EVMs. Let's say that the first ones to build ZK EVM, they like ZK single scroll, they had to use quite complex approaches, which is either you are writing ZK circuits by hand, or you are compiling a higher level language like Solidity to assembly code that can be proven. So that's, for example, the ZK sync approach. You take the Solidity compiler, and then you have like an intermediate target, and then you compile that target to something that you can prove. The problem with that is, in the first case, it's not very scalable to write all the ZK circuits. It's not very secure. I mean, it can be secure, but there's not a lot of people that are competent enough to audit these secrets, and it's hardly maintainable. In the second case, it actually leads to some incompatibilities with the default EVM spec. So for example, if you do like a create transaction on zk-sync, the create2, the created address is not the same as the one you would expect from the EVM spec. And that might sound minor, but when you're developing an app that is deployed across chains, you always want to have the most simple flow possible, which means you would like to have the same address on all chains. And if you don't have full EVM compatibility, this can be like a serious problem when developing, and it makes bringing multi-chain apps to your network a lot harder. But now we have a new way of building zk-VMs that was demonstrated first as a proof of concept by RIS0 last year, where they basically took an existing execution client like Reth. They used Reth as the starting point, and they used the RIS5 instruction set, compiled Reth to RIS5, and then they were able to prove the code that they compiled to RIS5, which means you can take basically any Rust code written in general purpose programming language, compile it to an instruction set that can be proven, and prove that instruction set. So this is great because you're actually approaching building zk-VMs with an engineering-first approach and not with a cryptographic-first approach. And that makes maintaining zk-VMs super simple. Like, Reth is getting updated, then you can natively benefit from these improvements and prove these updates. The only problem with that approach is Reth was not built to be proven. And the compilation to RIS5 is not necessarily the most efficient approach that you can think of. And that's where Kakarot comes in, because Kakarot is designed to be proven from the first principles. Why? So the first thing is the tech stack. Kakarot is using the Starkware tech stack, the Starknet tech stack, which is composed mainly by the Karo VM. So the Karo VM is one of the first zk-VMs that was put in production, and it has secured Ethereum L2s for over 4 years now. One of the most major use cases was a StarkX, for example, DYDEX. That was one of the most successful scalable solutions available a few years ago when it comes to DEX trading. The thing is, DYDEX and StarkX was not a general purpose L2. It was very specific to trading operations. But the thing is, if you want to have general purpose computation and benefit from people building any kind of apps, you want to have a general purpose L2. And if you want to have a general purpose L2, then you have different solutions. Either you go the EVM compatible way, or you go the non-EVM compatible way. If you go the non-EVM compatible way, then you don't have the tech burden of the EVM, and you can innovate on what you're going to build. And this is the path that, for example, Starknet have chosen. The problem is that like 95% of stablecoin supply is actually on EVM chains. So if you're not building for the EVM, you kind of miss on all that TVL and all that activity that your network could generate. And so Kakarot reuses the Starkware tech, but uses it to build an EVM compatible software. And so the thing is that you can take a high-level programming language like Cairo as an engineer, and you can write an EVM. You just follow the EVM spec as Cairo, and your EVM becomes de facto provable. You can just run it and generate an execution trace, send it to the stone prover, and prove your trace. And because Kakarot is made to be provable, that means you don't have a lot of inefficient operations, because we have thought about how to build Kakarot by removing unoptimized operations that were not strictly necessary for the provability of the EVM. And we also made sure to make the computations as friendly with the underlying zk-VM as possible. And that's possible because unlike the RIS0 approach, we're not taking a standard code base and making it provable. We're thinking about it when we're building it. So let's take a look at the standard example of a zk-VM flow. Basically, you have like a user that sends transaction to a regular EVM client. That could be Geth, Reth, Bezu, or even Kakarot in the future, although for now it's not fully compatible with L1 requirements. The RPC is going to send the transactions to a node, and the node is going to execute it and execute the transaction in the EVM. The state is going to be updated, stored in the DB. And you can actually do this quite fast because you don't really need to prove every transaction in real time, although that's the standard we like to see pushed in the future. So once you have sent all your transactions, you can wait for thousands of transactions or thousands of blocks to be processed, and you can batch them all together every once in a while and send them to a prover synchronously. And that prover is going to batch all the blocks that you have to prove, compute the new state root, and prove that all the transactions were valid, and send that proofs to verify-1. So far, it's pretty standard. And the way Kakarot is doing that is, the first product that Kakarot is making is building a ZK EVM on top of a StarkNet. So the architecture is slightly different, but the end result is the same. So a user would just send a transaction to an Ethereum RPC, and the transaction would actually be converted to a format that is compatible with StarkNet. So what you have is, you just use regular EVM tooling like MetaMask, send your transaction to our RPC that wraps it inside a StarkNet transaction, and then we just send your transaction and what you have signed to an EVM interpreter. The EVM interpreter is just going to run the transaction data that you have sent inside a StarkNet smart contract. So you can actually deploy a smart contract on StarkNet that is an entire EVM interpreter that allows you to deploy contracts, run precompiles, do like complex EC operations, like EC pairings or any kind of operations required for ZK, and everything runs inside a smart contract on StarkNet. And then, like the proving is actually handled by the StarkNet chain itself, and the state updates are handled by StarkNet. And you just need that small component of the Kakarot EVM to prove any EVM transaction. So, because Kakarot is deployed on StarkNet, the first product, it means that you actually have two ways of using it. Either you go the standard EVM flow, but you can also think that because it's deployed on StarkNet, you can actually use anything from the StarkNet state. You can actually interact with any StarkNet contract. So that means, let's say you have an application on StarkNet that's working really good, but your users, they don't necessarily want to install new wallets. What you can do is, let's say you have your StarkNet call data to execute your transaction on, for example, one of the leading DEX, which is like a Uniswap v4 DEX called Ekubo. What you can do is just take your TX data, convert it to EVM bytes, and then we can implement inside the Kakarot EVM custom precompiles for execution optimized for StarkNet. And in that case, you can just, we have developed a precompile that allows you to call any StarkNet contract from the EVM, which means StarkNet is now multi-VM, and you can use it from the EVM side, from the StarkNet side, or both together. So we're still in testnet. Our mainnet launch is planned for next month, but we're seeing good tractions with more than 100K active addresses, more than 100K Twitter followers, more than 1 million transactions processed. And this is good, but it's only the first step towards our vision of EVM probability, because with one code base, we can actually have 4 different use cases. The first use case is what I just presented, making StarkNet EVM compatible and multi-VM, but it's not the most exciting one. Once we have EVM available on StarkNet, we can start selling ZK EVM app chains running the StarkNet stack. And once we have that, we can actually start thinking about how do we make a general purpose EVM backend for proving blocks. And that's going to be very interesting because it's super aligned to the vision of having real-time block proving at the protocol of Ethereum. Like Ethereum could just, block producers could produce blocks, compute the proof of the block computation, and send that proof along with the blocks to other nodes of the network, which would only need to verify the proof to attest that the block was computed properly. And because Kakarot is designed with this provable approach in mind when engineering the code base, that means we could get a really good approach to real-time proving, and we think that our solution, whose benchmarks will be public next month, our solution is probably going to be a 10x improvement of the state of the art of EVM proving right now. And of course, what's also really interesting is how to make a ZK EVM running on top of Bitcoin. So we're working with Starware on that. Starware is pushing a lot of research on how to use OPCAT to have Stark proofs verified on Bitcoin. And if you have followed, you know that Kakarot is deployed on Starknet mainnet, and you can launch ZK VMs using the Starknet stack. So that means if OPCAT is enabled on Bitcoin, any Starknet chain can be settling on Bitcoin. And if you settle a Starknet chain on Bitcoin and that Starknet chains run the EVM, that means you can actually have a ZK EVM working on Bitcoin with no security compromises. Thank you. If you have any question, feel free to ask. Yes? So there are actually two different reasons why we think that. So the question was, sorry, can you?
Yeah, you mentioned that your ZK EVM would be much more performant than any other ZK VM currently in production. So what were the reasons for that? Is it because it's going to use Darknet and its Circle Starks and other proving infrastructure, or is it something else?
So there actually are multiple components to why we think that. The first one is that, as I said, we thought about designing Kakarot from the provable approach, which means that when you're going to do EVM block proving, you basically take an input, which is the sparse Merkle tree of the state that's going to be changed during the block, and the transactions to run. And the output is the new state tree and the change state. And the good thing about Cairo is a language that expresses assertions on memory cells. But the memory cells themselves, they don't really have to be, like the computational intensity of calculating what's going to be put inside these memory cells is not done at the Cairo side, it's done by the prover. Which means from the point of view of Cairo, you're only verifying whether some constraints inside your memory are holding. It's actually a language to describe constraints. And when you think about this, when you're building several components of the Kakarot EVM, you can actually think of clever ways of how do you design each component so that you are making the least amount of operations in the Cairo language, and you let the prover fill the memory, and you don't let the prover fill the memory with something that would not be sound or that would not respect the specification. So when you have that in mind, you actually have another approach to building a ZK VM than just like you would do in Rust, because you're taking advantage of the non-deterministic memory approach of the Cairo VM to only prove the assertions that you're making. And so the hard work is done by the prover, and you're only in your trace generating these assertions. So that's the first step of why we think it's going to be a lot better. And the second one is, of course, that the Stu prover is going to be the best prover on the market, probably for a few months, years, or I don't know how long. But compared to the current state of the art, so today we already are seeing good results. We've run simulations of, for example, how much does it cost to make an ERC20 transfer on the Starknet mainnet. It's on par with other competitors. But if you make that cost go like 100x cheaper or 1000x cheaper, then we're going to see a lot of improvements. And if you remove the Starknet component that I presented and just keep only the block proving system, then you can have a lot more optimizations possible, which will lead to that performance increase.
Okay, any other questions for Mathieu? Did I say that right? Mathieu?
Yeah.
Mathieu, okay. You know, in Canada, it's Matthew. Okay. Thank you so much for your time.
Thank you.